Hello and welcome to my presentation. I am here to walk you through my research and analysis on the daily stress and lifestyle. The contents include introduction, training opaque model, interpret model using model agnostic methods, and discussion. Let's start with the first part. Stress is a normal reaction to changes in the body resulting in physical and emotional reactions. Due to the rapid changes in modern people's work and environment, as well as the past pandemic, many people have experienced long-term and chronic stress, which have a serious impact on our life. The primary goal of this research is to investigate various factors that influence stress levels, then apply the machine learning model to predict the user's daily stress level based on their lifestyle. The research would implement exploratory data analysis method, predictive regression algorithm, and model agnostic methods to achieve the goal, and determining the features that have a substantial impact on stress levels. I hope this can make good use of these findings to guide people to reduce their daily stress levels effectively. In this study, I used the lifestyle and well-being data published on Kaggle. This dataset contains 15,977 survey responses spanning from July 2015 to March 2021, with 24 attributes describing how the survey participants live their lives. This study would mainly look at the following attributes: gender, places visited, sleep hours, social network, and personal achievement. These attributes are chosen more out of habit and lifestyle preference. For data preparation and cleaning, there are a few characteristics. The 4 lifestyle attributes are measured at a ratio scale because they can be counted, ranked, and quantified. The gender attribute is categorical, so I replaced all female with 0 and male with 1. The dataset contains no missing values, which is great. There is one row with an inconsistent data value format, which I decided to drop because removing it would not affect our analysis since our sample size is large. Before the prediction, at the very beginning, I did some exploratory data analysis to get an overview of the dataset, a quick walkthrough, describe method to find sleep hours, enjoyed the highest mean and median and the lowest volatility among all the numerical attributes, used box plot to graphically see there is no large outliers, and heist method to see the data was not drawn from a normal distribution, then examine the relationship between each 2 variables of the dataset through a correlation matrix, which was graphically displayed in a heat map, and we can see that the correlations between the target variables were all below 0.3, so there was no clear linear relationship between each 2 variables. At this point, we have a general understanding of the data, and it's time to move on to the modeling phase. So which model to choose? Since the linear relationship between variables is not obvious, it is best to deal with models that deal with nonlinear relationships with good performance. The dataset is large, and I was intent on determining which lifestyle elements have a significant impact on stress levels, so I hope it can have accuracy in predicting results as well as generalization ability. I finally chose to use random forests to make predictions, which can also improve the generalization of prediction by constructing multiple trees and combining their result. In terms of strategy, I selected features as social network, achievement, places visited, sleep hours, and gender, and set predictor as daily stress. Then split the data set into 80% of the training set and 20% of the test set. To optimize the model, I would use grid search CV to optimize the hyperparameters of the random forest regressor containing number of decision trees, maximum depth, minimum number of samples required, and number of features to be considered. Grid search is used to systematically traverse all parameter combinations. And for each combination, it evaluates the model performance using threefold cross-validation and selects the parameter with the best average performance after training and evaluating each parameter combination. Then for evaluation, I would perform model evaluation by analyzing 4 statistics: mean absolute error, mean squared error, and root mean squared error. Now let's get into the modeling. To get a random forest model, the first step I called random forest regressor and fit my data to get an original random forest. The evaluation value is shown in the figure. We can see that this random forest model can predict the target variable to some extent, but there is still room for improvement. The high MSE and relatively low MAE indicate that the model may not perform evenly across instances. The second step is to find out the max depth that minimizes the error by tuning as shown in the figure. Displayed the change in error while increasing the max depth of the model. The MSE dropped first to reach their minimal values at 6. Then I did the cross-validation by invoked grid search CV method and found that the combination showing in the figure was the optimal hyperparameter combination of the model scoring based on the negative MSE, and MSE was reached its minimal points when max depth was 6, which matched the result generated from step 2. Lastly, I used the best combination and the tuned optimal random forest model showing here, as we can see new error down from what it was before. So how to explain this model? The first thing I did was to use the random forest model feature importances method for the study. This method is calculated by observing the use of each feature in the decision-making process of each tree, reflecting the degree of a feature's contribution to the improvement of the model's prediction accuracy. Through the bar graph, we can see sleep hours is the most important factor, but overall there is not a great difference between features. From cumulative importance line chart, we see that all features except social network were essential to maintain the cumulative importance exceeding 95%. Sleep hours and places seems the most important as they contribute the most to cumulative importance. The problem here is obvious. We call the feature importance function of the random forest model and then return the importance score, but there is no clear explanation of why a feature is important. It seems to be still confusing. The rationale behind this is difficult for publics to understand and explain. So to better explain this complicated model, I will apply two model agnostic methods to explain, which are global surrogate and permuted feature importance. Since random forests are made up of multiple decision trees, I intend to transform it into a decision tree model, to utilize a global surrogate model, to provide explanations and insights into the predictive behavior of the original model. Firstly, I generate predictions using the tuned random forest model. Then I split the predictions into train and test sets and use the split data to train a decision tree as a global surrogate model. This decision tree model will use X-train surrogate as input and the prediction from the random forest, Y-train surrogate as target variable. But as you can see, the current model yields graphs that are too complex and may be overfitted. So to get a clearer view of the tree and to seek an optimal balance between model simplification and performance, I performed a cross-validation tuning using essentially the same steps to obtain the optimal combination of hyperparameters shown in the figure. Lastly, I fit a new model DTR2. These errors are checking how accurately the decision tree simulates the predictions of RF2, and we can see that the value is very small, indicating that this decision tree substitution model can simulate the predictions of the original model effectively. At this point, we have transformed the complex random forest model into a more intuitive decision tree model through global surrogate. Next, I drew this decision tree model, which allows us to approximate and interpret the predictions originally generated by the random forest. Through the model, we can see that the topmost node highlights sleep duration as the main factor affecting stress levels. The threshold of sleep duration, 6.5 hours, divides the data into two major categories, reflecting the importance of sleep on stress. Going down to the next layer of the tree, gender becomes the second decision point, suggesting that there may be differences in the factors affecting stress levels between men and women. As we continue to look deeper into the tree, we find that the number of places visited is also an important factor affecting stress levels. Each node provides a stress level prediction value based on the branch of that condition. These values give us an intuitive understanding of how various combinations of lifestyles can predict stress levels. Comparing it to the previous conclusions of the random forest, and it's obvious that the decision tree model provides a clear framework to understand complex data relationships. We can see clearly how each feature affects the model's decision-making path. This makes understanding the model's behavior more direct and allows us to focus our attention on the most influential factors. Currently, our ranking of the impact of feature values is obtained by calculating feature importance, which ultimately has opaque characteristics. My next step will still focus on feature values, but will use a more transparent method to explain their importance, namely permuted feature importance method. This method measures the impact of perturbation on model performance, I am using RMSE here, by randomly shuffling the values of each feature. The process involves training the model, assessing performance, shuffling individual features, assessing the change in performance. The greater the performance degradation, the more important the feature is. Out of curiosity for new technology, this time I learned and adopted the RapidMiner software for analysis. My process was as follows. First, I imported the cleaned dataset into the software and constructed a standard random forest, which resulted in a performance as shown in the figure. The RMSE is 1.326. Next, I shuffled the values within each feature. This is the process of measuring sleep hours. My method was to extract all the sleep hour data, assign random index numbers to them, and then sort them. At this point, the sleep hour results were shuffled. After that, I joined this new feature data with the original data to form a new data set and apply model. Using the same parameters and process, I obtained all performance after shuffling for each feature. The results obtained are shown below. Remember, the greater the performance degradation, the more important the feature is. So after comparing and ranking the results, I found that sleep hours, gender, and places visited remain the most influential factors. Although sleep hours no longer has a dominant position, this outcome is essentially consistent with my previous findings, further enhancing the credibility of the earlier results. I also conducted tests using Shapley value and Lime through RapidMiner, and the results are as shown in the figure. I will not explain each detail due to time constraints. There is limitation of the UI. It only displays the top 3 most important influencing factors for each data point, and it's difficult to summarize a conclusive result from this, but it is still of significant reference value in the process of analyzing and studying opaque complex models. In conclusion, we have applied a random forest model and enhanced its interpretability through 2 methods, global surrogate and permutation feature importance. The analysis indicates that gender, sleep hours, and the place visited are key predictors of stress levels, suggesting a strong influence of these factors on the perceived daily stress. However, there are limitations to this research. The research trained only one random forest model and calculated errors, which does not guarantee it as the best model. And the value in dataset are scale ratios with a small range of values, which means the differences in impact between factors are not large and may not fully reflect the complexity and nuances of social issues. Looking ahead, to improve the robustness of the study, we can train various models, such as ordinal logistic regression and bagging, and determine the best predictive model by comparing MAE, MSE, and RMSE. Moreover, methods like leave one out cross-validation can be introduced for more robust error estimates. Also, to gain a deeper understanding of how different lifestyles affect daily stress levels, the study can incorporate more features for further research. Remember, sleep well and travel often. Take care of your stress levels. That's all for my presentation. Thank you for your listening.